Alright, so here we have a question about a golf ball being launched at 40 meters per second at a 50-degree angle above the horizontal. So you can see I just created my 50-degree angle here, and I'm going to go ahead and fill in the rest of these things. I'm going to label it that it's 40 meters per second, um, and then I'm going to go and I'm going to uh, label things that I know. I'm going to list my givens here. So the first thing that I'm given, or that I know, is that there's no acceleration in the x-axis. Remember, the only force acting on the projectile is going to be the force of gravity. Therefore, I know there's no acceleration in the x direction, and my y acceleration is going to be negative 9.81 meters per second squared. So next, I'm going to solve for my VIX and my VIY. And I haven't drawn those vectors yet, but I'm about to. So here, I'm going to draw my vectors for Vx, Vix, and of course my VIY. Now that I've drawn those in, I can see what kind of functions I'm going to use in order to figure out how to solve here. So I have a 90-degree triangle, so I'm going to go ahead and use the cosine function to solve for Vix. So Vix is adjacent to my 50-degree angle, so I'm going to use cosine. So Vix is going to be equal to Vi, the 40 meters per second, cosine of 50 degrees. So that's what I'm doing here right now. I'm just typing it. I will make it bigger in a second so everyone can see. And I didn't have a tablet to do this. So I'm filling in right here. So the VI was 40 meters per second, and then my cosine 50 degrees. I calculated this, and I got that it was equal to 25.7115 meters per second. Now, I'm going to eventually make that into significant figures, but first thing I'm going to do is I'm going to calculate my VIY. Now, my VIY is opposite, so I'm going to use the sine function. And when I calculate this, I end up getting the answer to be 36.6418. Or, I'm sorry, 30.6418. And now I want to change this so that I have the proper significant digits in each one of these. So my initial number is 40 meters per second. I'm going to go ahead and leave it out to the next decimal place so that my final answer will not be so far off. So I'm keeping 3 significant digits even though the final answer should have 2, but that's so that later calculations won't be incorrect. So now that I know what my VIX and my VIY are, I'm going to go ahead and put them into my table. So there's my VIY. And what else do we know now that we have these numbers? Well, I can tell you that the x velocity is not going to change. So I can copy that and I can put that in my VF for x. Remember, there's no acceleration in the x-axis, so that stays the same throughout. Again, my VIY will be negative of the 30.6. So my next step now is going to be to solve for time. Now this question didn't explicitly ask for time, but I know that I'm going to need it. Every problem that we're going to do, we're going to need to find time. So that's my next step. Okay? And there's a couple different ways that I can do this. I know that time is based on the height of my object. That means my y component. Because of that, I'm going to change these all so that they're the y components of each variable. Remember, time spans across both the x and y, so that one does not get a subscript. Okay, so the first way that I'm going to go ahead and solve this is I'm going to say that my VFY is going to be the same but opposite of my VIY. Okay, so the process is the same for both situations I'm going to show you, but the first thing I always want to do is solve for my variable here. So here I have subtracted VIY from both sides, and now I'm going to divide by AY in a second. So that I'll be left with an equation that gives me an answer that's going to be equal to t. Okay, so I'm going to divide by A sub y, and that is going to be equal to t, the time. Now this is the first one I'm going to show you is going to be equal to our total time. So therefore I'm going to replace VFY with a negative 30.6 meters per second. I'll fix that. Okay, negative 30.6 meters per second. And that's because on the way down, the V final in the y direction is going to be the opposite of the VI. So here I have negative 30.6 meters per second minus 30.6 meters per second, which was my VIY. And then I'm going to divide that whole thing by negative 9.8 meters per second squared. And that'll give me an answer of time. And the time is going to be equal to, I believe 6.24 seconds. So here I have, 6.24 seconds. Okay. I also know that I'm going to need the half time eventually, but I'm going to go ahead and paste this up into my chart here, 6.24 seconds for the total time that the ball is in the air. Now my half time, t half, is going to be just half of this time. So why do I need that? Well, that half time is going to tell me the time it takes for the ball to reach its maximum height. That's why that number is important. So the half time is 3.12 seconds. Now that was just one way that I could solve this problem, so I'm going to make that smaller and I'm going to show you a different way here in a second. I'm going to use the same formula, and remember this formula is derived from the formula A, the average acceleration, equals the change in velocity divided by the change in time. So those two formulas are synonymous, but remember I just rearranged that formula to get this. So the one that I'm doing now, the is I'm going to just solve for the half time. So that means my VF, which is going to be at the top of that apex, is 0 meters per second. And this is going to give me my half time. So the same process here, 30.6 meters per second divided by negative 9.8 meters per second. That's going to give me my half time. And you'll see once I do this, and once I calculate this, that I will get the same answer as I did for the half time above. Okay, so here I'm just rearranging my formula again, so that I get negative 30.6 meters per second divided by negative 9.81 meters per second squared. Now, just to make sure that my answer is going to be what I'm looking for, I'm just going to talk about the units for a second. So meters per second divided by meters per second squared. When I copy, change, flip all that, I'll have an answer with units of seconds. Okay, so here I have solved for the half time, which is 3.12 seconds, and to get the total time, I get 2 times that half time, which was 6.24 seconds. Again, this is the same answer as I previously got before. So you can see that it is the same answer. So 2 different ways, the same answer. Okay, next, I want to solve for my dy. To do this, I'm going to use a formula right off the reference tables. That is, I'm going to start with the basic form here. D is equal to VIT plus 1/2 AT squared. Now, you might have it written down as DF equals DI plus VIT plus 1/2 AT squared, and that's fine too. Our initial displacement in both the x and the y direction is 0, so I just got rid of that term. Here I'm adding the subscripts y to denote that we're going to use all of our y variables. So I'm going to go ahead and substitute in for this. dy is equal to the 30.6 meters per second times, now here I'm going to use the half time. Again, we're looking at for the maximum height. That's what dy is. So maximum height takes half as much time to get to that point. If we're looking at the parabola shape that it makes, it only takes half the time from its total flight to get to that max point, that apex. So I've used the half time. I'm just substituting in with units, And this is supposed to be squared. I'll go back and fix that afterwards. You'll see me fix that. But I did, when I typed it in on the calculator, I did square that term. So this is the correct answer. Okay, so here I just wanted to point out that the units work out in this. Okay, meters per second times seconds, that gives me meters. And then for the second term, meters per second squared times seconds squared gives me meters. So that's why I broke those two up, to show you that the units work out in this. So we're going to get an answer, a distance in meters. So I have 95.472 meters subtracted by 47.7472 meters. Again, this was the correct answer, even though I didn't write that it was squared up there. I did square it on my calculator. So dy, final answer, is going to be 47.7248 meters. Now again with sig figs, I'm going to say that it has 3 sig figs, and I'm going to say that my answer is 47.7 meters. Okay, so now that we've done this, we can go on and solve for dx. So I've just copied the equation from above, and we're going to solve for dx now. And I'm just going to repaste the formula, and I'm going to replace those y's with x's. I don't want to use the formula that has changed at all. So sometimes we'll have a formula where vi is 0. We have to start from the beginning when we're reusing formulas. So some people, when they were doing that project yesterday, they had that the formula for dx was dx equals 1/2 at squared. That's not the case. Or they had dy equals just vit. Again, that's not the case. We have to start from the original form. So here, I can get rid of that 1/2 at squared term in the x direction because there's no acceleration in the x direction. So I'm left with dx equals vix t. My vix, as you can see above, was 25.7 meters per second times, this time I'm going to use the total time to be able to find the total x distance that it traveled, so 6.24 seconds. When I calculate this out, I end up getting the range for the dx is equal to 160 meters, which I'll show you. This is what I get before I have sig figs, and this is going to be the answer for after I have sig figs. As always, the very last step to solving any equation is going to be to ask myself, does this make sense? So I'm going to go through and show you that it does. I have the units that I wanted. The units worked out to be meters, and I know that my dx should be bigger than my dy in this case, because the range is going to usually bigger than the height. Here I'm just changing it, so I denoted that I did in fact square that 3.12 seconds when I did my calculations. Okay, so let's go back into the top and see if all of our answers make sense. Well, I have a 50-degree angle here, and across my 50-degree angle is VIY. VIY ended up being bigger than VIX, which makes sense. This angle up here would be a 40-degree angle, so I would expect that across from the 40-degree angle would be a smaller number, which is the case.